All right, so I've got a pump operating at steady state. It draws water from a pond and delivers it through a pipe whose exit is 90 feet above the inlet. At the exit, the mass flow rate is 10 pound mass per second. It tells us that there is no significant change in the water temperature, pressure, or kinetic energy from the inlet to the outlet. The power required by the pump is 1.68 horsepower, and you'll notice that there's a negative in front of that. And we want to find the rate of heat transfer between the pump and its surroundings in horsepower and BTU per minute, and we're told what the gravitational constant is. First thing I'm going to do is to draw my imaginary boundary around my system. So you'll see it encompasses not only just the pump, but also the piping from between that delta Z. And let's see. So the first thing I'm going to do is apply my conservation of mass. The dmdt goes away because it's operating at steady state, and because there's one inlet and one outlet, the mass flow rate m.1 and m.2 are equal to one another. Then I'll apply my conservation of energy. I know the dEdt goes away, but let me think about the typical assumptions that I make for a pump. So typically we say steady state, Q dot's equal to 0, changes in kinetic and changes in potential energy are 0. But let's just pause for a second because it's asking me to find what Q dot is, so I don't want to ignore that. The change in kinetic energy, there's nothing in fact, it tells me point blank that the kinetic energy from the inlet to the outlet, there's no significant changes. And then I look at the potential energy change. Now, typically, we're applying our conservation of mass. If we're looking at just the pump, if you just draw your control volume, your system boundary around the pump itself, no, there's not a significant delta change in potential energy from the inlet to the outlet. But the way we've drawn our control system, our boundary, we see that yes, we absolutely do have a change in elevation, a change in potential energy, because our system encompasses not just the pump, but the piping from the level of the water all the way up to 90 feet. So I can't ignore those things. So really the only thing out of that I can ignore is the change in kinetic energy. So you really kind of have to look at what the problem is asking you to consider before you decide just to ignore it completely. So I've done all those things. Here's what I'm left with for my first law. I've got one inlet, one outlet, so I can just get rid of those summations and put some subscripts 2 and 1 on there. And I rearrange things to get Q dot. And then I put my H values together. And that delta Z is Z2 minus Z1. So just kind of simplifying it even a little bit more. Now the H1 and the H2, it's the enthalpy at T1 and P1 and the enthalpy at T2 and P2. But if I look at the problem statement, it tells me that there's not a significant change in the temperature and the pressure. And so if the temperature and pressure, if T1 P1 is approximately equal to T2 P2, then H1 and H2 are going to be approximately equal as well. And so those two things, H1 and H2, if they're equal to one another, then those things are going to just, that's going to go away. And now it's just a matter of plugging things in, watching my units, and I get negative 0.05 horsepower. And of course, I can convert that to BTU per minute using the appropriate conversion factors as well. So I hope that was helpful. Thank you for watching, and let me know if you have any questions.